but it appears starting at 8 o'clock is going to be a tough one, right? Because just getting into the room is a little challenging. All right, this this is supposed to be a lab. Obviously, it's not going to be a lab out there. I'm going to kind of go ahead, since our first lecture was preempted by a holiday, I'm going to go ahead and do the first lecture today. The only problem is I have to do it twice, because the other half of this class I do it tomorrow out there. So I didn't print off an attendance sheet, so I'm going to pass around a sheet, but tell you what, I'm going to pass it around, but maybe you might want to hold on to it for a little bit, turn it in at the end of the class, right there. Okay. And I don't have a pen. Probably have one in my bag. If I seem a little disorganized, it's because when I got here this morning, I could not get into my office because they locked the doors at the elevators. So I had to bring everything here and set up here. So I had to run down that thing. Okay. My name is Iskanda Hack. I'm the lecturer for this class. I am brand new to UniKL this semester, so some of you probably have heard stories about me. Some of you probably haven't. I'm actually going to try recording this lecture and see how that works out. So when I say recorded, you'll see what's on my computer screen when you watch the recording and hear my voice, but you won't see me. But what I discovered when I record lectures, students don't want to see my face anyway. They want to see what's on the on the PowerPoint slides or in the demos. Oh, there's the rest of the class. Come on in. Microcontrollers, right? And they're facing. I knew that I was going to get by I was getting by too easy. Come finals, I was going to have an easy time with it. Just all the bigger the class was. So, okay. I'm going to be doing things a little bit different. The book, I believe, is anybody log on to the e-learning site for this course? I believe I already put the book up on the site. But I'll go through the book a little bit. There's multiple books I'm using. I think last year this class was taught using a PIC processor. I'm going to be using the 8051 microcontroller right there. And I've ordered, hopefully they come in before too long, 20 development systems and when I say development systems, we're talking pretty bare bones development systems. It's basically a programming module. Come on in. I think the general rule is I may start at 8:15 just simply so I can eat breakfast before class. So let me just kind of jump in here, and the syllabus for this class looks like this right here. I put my phone number up here. I appreciate it. That if you want to send me a message saying you're not going to be in class or something like that, you go ahead and don't be calling me 11 o'clock at night, 12 o'clock at night. I turn my phone off. So it's one of those interesting things The rest of this is standard mumble jumble for course syllabus. Oh, everyone is coming in late. 8 o'clock classes here are just like in the U.S. Nobody shows up at 8 o'clock. Nothing changes. You go halfway around the world, nothing changes. An 8 o'clock class is still So this is the right course number, right? Everyone's in the right place, right there. No one's in here thinking that they're taking power electronics or something like that, or three-phase machines. So, okay. Let me just jump right here, right there. This is all standard mumble jumble from syllabi. What these really are is transferable skills. We say that we're going to teach you some teamwork in this class. Basically, you're going to work in lab groups. That's your teamwork You're going to learn some communication skills. I'm probably going to make you do a presentation or two, at least myself. I don't know if I'll make you get in front of the whole class. That's always, people dread that, don't they? You don't think about the professor has to stand in front of the class every day, but even when I was a student, I dreaded giving presentations, and then I ended up doing this for full-time for a living. The main thing is problem-solving skills. My approach is a little bit different because I look at this and want you to understand the principles and not study for the exam. Unfortunately, the way that our curriculum is set up here, 60% of your course grade is going to come from the final exam. That's just the way ICO is set up. Therefore, when I start to write the final exam questions, they're going to be written in such a way that you're going to need to understand the material, not just memorize. That's there. And one of the things is that I will tend to ask open-ended questions. Don't leave questions blank when you take quizzes and exams. Be sure to try to answer everything, but we'll get to that later. There, so that's there. Mode of delivery, that is not right. I was told I couldn't change much on the syllabus. It's lecture, discussion, presentation, tutorial, and demonstration. Is that somebody else's phone making noise? That there. I don't believe in doing demonstrations. I'm going to be making you run the software and download code into these boards and see what's going on. Unfortunately, the microcontroller boards we've got are very basic, so we can see what's going on. We can flash an LED, hook up a few things to the board, but it's not a very elaborate system right there. I'm trying to get that there. Phase test 1, 2, and mini project. Those are your, basically we're looking at somewhere around a third of the way through the course I would have a first test that's worth 10 points, 10 points for the next one. The mini project is basically a lab type project. Again, the boards we've got, we're going to be using, I didn't bring one with me, but I can't show you because I don't have internet on this computer. But they're only about this big. I mean, they're very small, but they've got an 8051 chip on there along with the I/O, and we can connect to them. One of the things I don't believe in is that's running simulations completely. We're going to be running things on the board. So, okay, enough with that there. The rest of this stuff is just mumbo jumbo. And again, this is the topics that are going to be covered, not necessarily in the order in which they are right there. Introduction, structured systems design, microcontroller architectures. I will be working this class predominantly from the viewpoint of C programming right there. I know last semester you took the 8086 microprocessor, and that was completely in the assembly language. Yeah, you can forget all that. No one uses assembly language for programming 8086s, 8051s, or any microprocessor anymore. That's just too tedious and too big of a pain in the neck. What's that? No, not there. Well, actually, I'll talk a little bit about that later. This microprocessor comes from the same family as the 8086, but it's developed by the same people, so it's very similar in some ways and very different in other ways. We'll talk a little bit about the differences between microprocessors and microcontrollers. And really we've got 12 hours here on microcontroller interfacing. I hope that we can actually do quite a bit of that there. It depends on how much support I get from the lab with our development boards. The development boards we've got are very basic. Like I said, I don't remember how many I/O we've got on there, but there's probably enough to do at least. I know we could do the 7-segment displays, we can do the switches, the LEDs. I don't know if I could do full keypad. I'm not sure if I've got enough I/O. Actually, you only need 8 I/O. I think I have enough within But whether or not we have hex keypads that we can use Because one of the problems I've got is I don't know what's in the lab right now. Comment or just that there? So, okay. Let me just kind of jump into the PowerPoint. Today's here is going to be basically a very, very brief introduction right here. Hopefully it works out there. By the way, before I go any further here, let me stop this right here. Right here. The book should look like this right here. maybe. Why is it not coming up? It's a Scott McKinsey book. Why is Mike? Oh, all right. This doesn't make my life easy. All right. What I'm seeing here is two different view, zoom, page. Okay, this is the book. It should be on the e-learning website. If not, bring a thumb drive and I'll give you a copy. That there, you can pass it around. It's not quite legal to do it that way, but that's there. But this is probably the best book that I found in ebook form. I looked in the library. Most of the books they had were older, so this is the book I opted to go with. There's a couple other books that I've specified. I'm going to be working probably 90% out of this book. Today I won't be, but right there. But as you can see, it's that there. And from time to time, I may actually bring the book up here and just kind of use the slides from it. I won't read the book to you from the podium up here. That there. That's pretty boring for me to sit there and read it. But this is the book right there. But before I get into that, there's several things I need to do first, and that is, one is go back and review everything you should already know. Right there. So, all right. You know, whenever I bring PowerPoint up there, this changes my display here is different than this display here. So it kind of messes me up here. And what are we got going here? Okay, finally we're there. All right, these slides are actually from a different book, but it's the same basic material. That there. The first thing I want to kind of do today is just kind of go back and review everything you should have had the last 2 semesters. And I know some of you took digital, 2 semesters ago? That there, so your binary numbers are completely forgotten about since then. You probably didn't use a lot of it last semester, right? That there. So, and then kind of a quick review of digital. Now, a big difference between this class and last semester's course, which was strictly on the 8086, is you probably didn't talk about any hardware last semester, right? It was just the internal architecture of the 8086. You talked a little bit about how to interface it to memory. You know, I looked at the final exam. You didn't get into a lot that there. This semester, we're going to be looking at how we connect to the outside world. So we're going to be looking at things such as analog to digital converters, stepper motors, switches, sensors, those types of things. So we've got, you know, this course here brings the electronic side of it back to the microprocessor side, right there. So we're going to go a little bit on that there. So, all right, let me just kind of jump in here, and we'll go as far as my voice goes. I've got a little bit of a sore throat. Actually, I'm going to probably take MC this afternoon and go see the doctor. So don't get too close to me. That there. I had a sore throat last time. I was running a little bit of a fever, so that there. So, all right. Number systems. I know that you talked about number systems in the past. I'm going to talk about them again, because when we look at the microprocessor, the microcontroller, the digital world, numbering systems comes into play huge. We use base 10. The reason we use base 10 is because we have 10 fingers. If we were born with 8 fingers, we would use base 8. There's nothing magical about base 10. It just happens to be we were born with 10 fingers, therefore, or most of us were. There's a few of us that were not, but most of us are born, you know, with 10 fingers, so we use base 10. That's there. So we have our symbols 0 through 9. That right there. 10 symbols up there. So the early numbering systems, the early Indian number systems that they only had 9. It was the Arabs that introduced the 0 to the numbering system that happened to put everything together and allow us to do things like add, subtract, multiply, and divide. That there. If you have something other than a numbering system, you cannot add, multiply, or divide. Right there. So one of the things that I'm going to talk about here briefly here is, let's just say we live in a strange world where we don't have 10 fingers, but we have 7. Right there. And let's just kind of look at what that numbering system would look like and how it would relate. And we talk about, in the digital world, we talk about base 2. Right there. Later on, we're going to talk about base 16, and that'll be later on this morning here. We'll talk about base 16, and I'll talk briefly about base 8. But for right now, I'm just going to make up a numbering system, and that's going to be base 7, right there. Right there, and I need to fix this here. Right here. The problem is this particular projector is so old that it's a different resolution than this here. So every time I bring up PowerPoint, it disconnects the two of them up there. Okay. All right, we don't want this. We want just one note. I don't want this button. Okay. This is not going to work here. Why is my one note not working? I don't want to use a cloud. Up there. Well, maybe I won't be able to use OneNote here. My problem is that this particular room does not have working Wi-Fi. I don't think that I can use. Okay, here we go. All right. Okay. So let's kind of talk about base 7. Base 7 means we got symbols 0, 1, 2, 3, 4, 5, and 6, right? That's all we have. Now, before we talk about base 7, let me kind of go back and hit up something on base 10. And this is the way all numbering systems work. And I'm not sure if this is the approach you had before, but it's the way I like to look at it. If we look at base 10, that there, base 10 right there, we got the number 4275. Base 10 right there. That's there. This column here is the 10 to the 0 column right there. This is 10 to the 1s column right there. This is 10 squared, and this is 10 cubed right there. Now we know this as the thousands column right there. We know this one here as the hundreds column. We know this is the tens column, and we know this is the ones column. It just so happens that we're used to dealing with it there. But when we look at other numbering systems, we have to look at this pattern right here. That there. So when we look at our base 7 situation, our numbering system is going to be our 7 to the 0 column, our 1s column, our 7 to the 1s column, which is our 7th column, our 7 squared column right there, which is 7 squared right there, this there, and then 7 cubed column right there. So those are the 4 columns that we have that there. So when we look at any number in base 7, right there, let's just take the number 4235. That's and I'm going to put the number 7 there to show that's base 7. What does that equal to in base 10? Is that there? And the way you would do that is you would just simply add up the value of each one of these columns right there. So it's 5 times 7 raised to the 0 power, which is equal to 5, right? 3 times 7 to the 1 power. 7 raised to the 1 power is 7, right? Right there. So that is equal to 21. 2 times 7 squared. 7 squared is what, 49? Get there. So 2 times 49 is 98. And this is where I'm going to need help because I can't think 7 cubed. But what 7 times 7 times 7 is what? And then 4 times that. And what's that? 340. I had a calculator here somewhere. I'm rather disappointed that the calculator that they now have is a completely different calculator. So 7 times 7 times 7 equals 343, and then times 4, right? So 1372. Equals, and we just add those up right there. And we don't really have an easy way of checking that, but that's the way that we would add those up right there. You know. Right there, so when we add those up, so that's 5 plus 21 plus 98 plus 1372, 1496. So the number 4235 base 7 equals 1496 base 10 is the way that we would do that right there. I'm not going to worry about going in the other direction. We almost never would do that, but that's the way that you would look at any numbering system. Now we can add 2 numbers up in base 7 and they would still add up the same. The only thing is we would carry once we got over 7 that there. So if we added 2 numbers right there, if we added 2 numbers, say for example we added the number 35 3 plus 32, those are both legit base 7 numbers. When we add 6 to 2, what's that equal? 8. 8's an illegal number, right? So that's going to give me a 1, and we carry a 1 here. Right there. So 6 plus 1 is 0, because that's a 7, that's when we carry. But 6 plus 2 is 8, so that's a 1 with a carry 1. And it gets relatively confusing, but when we add 6 plus 1 equals 10 base 7. 6 plus 2 is equal to 11 base 7, right there. Right there. So Numbering systems can get confusing. That they're all you really need to worry about at this point is what defines a numbering system. That's there, and that is the first column is whatever your base is raised to the 0 power. The next one is whatever your base is raised to the first power, which is actually the value of the base. The next one is the base squared, base cubed. Now, if we go the other side, it works the same way. Now, that there. If we go in the other direction, right here, right there. Let's say we've got the number, and I'm going to start with base 10, and let's say we've got the number 235.65 right there, right? This column here is 10 to the minus 1. This is 10 to the minus 2. So we look at this as our tenths of a column. If we're talking RM, this would be how many 10-cent pieces we have, and this would be how many 1-cent pieces we have. Except for they don't make the 1-cent piece anymore, do they? That one disappeared. It's, the smallest one is what, the 5-cent piece? Right there. But when you're talking that there, but this is our tenths column right here. This is our hundredths column. 1/100th of a ringgit. Right there. That's what 1 cent is 1/100th of a ringgit right there. So the same thing if we're looking at base 7 right there. If we take the number 235.65 and we're saying that's base 7, this is going to be 2 times 49, 3 times 7, 5 times 1, plus 6 times 1/7, right there, because 7 to the minus 1 is equal to 1/7, right? And then 5 times 1/49, right there. And I'll let you look at that there. So it goes the other way too, as you go to the other side of the decimal point, right there. So all numbering systems work the same way, right there. Now, fortunately for this class, I put it up there just to confuse you, just that there on the right of the decimal point. We won't be using floating point numbers in this class, so that there. But I'm just pointing out that that's the way it works to the right of the decimal point. The same with base 10. As you move to the right of the decimal point, it's 1/10th, 1/100th, 1,000th, 1/10,000th, 100,000th, 1,000,000th column. That there. You just keep going to the right of the decimal point. Each column, you divide the weight of that column by 10. If you're looking at another base, in this case I'm using 7. It's the 1/7th column, the 1/49th column, the 3/43th column, and we won't worry about right there. But you divide the value of each column by 7 as you move to the right there. Now, computer systems, right here, and let me close this out here. Maybe. Right there. Desktop, go back to my PowerPoint right there, and slideshow from current slide. And this is where things are going to get messed up again, right there. Now, computer systems have only 2 states. The way computer systems operate and digital electronics operate, you either have a switch can either be closed or it can be open. The way that we work it is there's transistors that we turn on or turn off, right there. And right there. So you only have 2 states, 1 and 0, right there. So we have base 2. So we end up with these long strings of base 2 numbers. Now, in all honesty, it's not practical to work with base 2 on a daily basis when you're dealing with computer programming or microprocessors or that there. We usually will go to another numbering system, which I'll talk about in a minute. That's there. But there. So what we look at, when we look at base 2, we have that there, and the slide will be posted online, but I'm going to actually go through and do it a different way. To divide a number to the decimal to base 2, I have a different way of doing it that's a little bit easier, I think, than this method that's there. So you will have to be able to go from base 10 to base 2 and vice versa. Now, to go from base 2 to base 10 is the same way, right there. And I'm sorry, but my computer, it's a setting that I have to change every time. That's there. And keep in mind, not only am I new, I actually just purchased this particular laptop not too long ago. I have a different laptop that I was using out there. I happen to like it because it does make it a little easier to out there. So when we look at a number, and let's just go at 10110010 out there, and this is a long number. When dealing with 8-bit with binary numbers, I always group in groups of 4, and that will become obvious why we do it that way there. You know, the most obvious reason is groups of 4, it's easier to keep track of. But when we look at microcontrollers like we're using for this class, the 8051 is an 8-bit microcontroller. Right there. In other words, each data word has got 8 bits to it. So that would be 2 4-bit nibbles. Right there. And 8 bits is referred to as a byte. And I'm sure you've seen those terms before, but I just kind of point out that there. Last semester you took the 8086. That was a 16-bit microprocessor right there. Now, you think that we're going backwards. In reality, we are going backwards a little bit. That's there. We're going to a lower power processor. That's there. But we're going to a lower power processor that does a lot more than just the 8086 right there. So it may be slower, it may be lower powered, but when you look at the actual IC, it does far more, and we'll see that later on. Because it's that there. When we talk about what a microcontroller is, that'll be evident. All right, so when we look at that there, the other is when we get into hexadecimal number, you'll see why we do that there. So when we look at this, it's the same thing there, and I'm just going to write it off to the right here. It's the 2 to the 0 column, which is our 1's column, 2 to the 1's column, which is our 2's column, 2 squared, which is our 4's column, 2 cubed is our 8's column right there. 2 to the 4th is our 16th column, and I'm sorry about that. There's a little button that I hit on the side here. 2 to the 4. 2 to the 5th. This thing is supposed to have an erase right there. Yeah. Okay. 2 to the 5th is equal to, wait, hold on. This is 16. This is 32. 2 to the 6th is 64. And 2 to the 7th is equal to 128 right there. So that's the value of each of our columns up there. The easiest way of doing this is because we're dealing with 0 and 1, you either add the number or you don't add the number. You don't have to multiply anything here. So in this particular case, we're going to add 128. We're not going to add 64 because that's a 0. We're going to add 32. We're going to add 16. We're not going to add 8. We're not going to add 4. We are going to add 2, and we're not going to add 1. So it's just simply going to be bring up my calculator again. I thought I pinned that to the start. put it to the taskbar. There we go. That'll make it easier. Flip left, right there. Right there. So when we do that, that's 128 plus 32 plus 16 plus 2 equals 178. Now, your calculators, I think, do binary to decimal conversions. I looked at somebody's calculator yesterday, and I think I broke it, so on Tuesday. I put it in some weird mode, so I'm not going to figure out how to do it with your calculator. The old Windows calculator, before Windows 8, actually had that built into it as well, but this particular calculator has got standard, scientific, and converter, but the converter is everything but data, gigabytes that it doesn't get into. It converts bits to megabytes, that type of thing that they're. So it doesn't have the programmer's calculator that they took that out of Windows 8. So I can't show you that is right off the top of my head. But does that work out right? That there. So okay, but that's how we do that there. Now to go the other way around, I think the other way around is just as easy, but the way that I like to do that there is, let's just take a number here, and let me first off, let's write our numbers here. Our numbers on the right: 1, 2, 4, 8, 16, 32, 64, 128. And there should be 1, 2, 3, 4, 5, 6, 7, 8. There should be 8 right there. Now, sometimes I make a mistake. Incidentally, I should tell everybody, if I make a mistake, don't be bashful, tell me. The last thing I want to do is get to the end of a problem and have the wrong answer and look foolish. I'd rather look foolish early. That there. So, that there. So, all right, let's take a number here. And what we're going to do is let's just take the number 193, right, for example, here. And we look down here and we find the largest number in here that I can subtract from 193. In this particular case, it's 128, right? So I'm going to put a 1 here. And I'm going to subtract 128 right there. So 193, subtract 128. So I got 65 left. Right there. So the next one I can subtract from that is 64. Everyone see that? So I put a 1 here. Subtract 64. I'm left with a 1. Right there. Can I subtract 32 from that? No. So I put a 0 there. Can I subtract 16? No. Can I subtract an 8? Nope. 4, 2, 1. So our binary number is 11000001. Right there. It's a fairly straightforward process right there. And I don't know did they teach that method before, or is it? There's many complicated methods. To me, that's the simplest method I've found, is just to do the subtraction right there. I don't bother with the divide by or anything like that. Just look at this column right here, and I'm pointing to this column here. If anybody watches the recording, this column. Well, let me just kind of point to it over here. I'm pointing to this column here, right there. Again, I just look here and I start off 128, subtract it off. 64, I subtract it off, and then the next one I can subtract off is the 1, and that's our number. And we could do this, forever and forever and forever. That there, but that's the easiest way to convert that there. And again, I know you've seen binary numbers, you've seen that before, but before I jump into the real material of this course, my approach is that I want to make sure that we're all on the same place starting that there. So, and does this ring a bell? You've seen this before, right? Is this refreshing your memory a little bit? That there. So, is it helpful? Be honest. If it's not helpful, that there. Is it helpful? Yes. Okay. Yeah. That there. Okay. By the way, we won't put this recording out on the public domain. It's only for students in this class to watch. That there. So, by the way, the reason I record this is I know that my English sometimes is a little fast. So it does give you the opportunity to go back and re-listen to that there. So that there. Okay, let me jump on to the next topic here. Right there. And close that and get back to, oh, pardon me while I try to figure out how to use my computer again. Okay. Right there. Okay. Oh. There. And now we wait for this thing to set there. Okay. As I said before, ignore this slide. I'll be quite honest, I stole these slides. I don't think that this particular method is as easy as the one that I used. But this method does work. I mean, there's just like any other way of solving problems, there's probably 15 different ways of solving problems out there. And one way works best for me, it may work, another way works better for you. I don't really care how you solve a particular type of problem as long as you get to the right answer out there. So, okay, and I'm going to skip through that whole discussion right there. Now, let's get to the heart of things here. This table here, right there, is a very important table. It's one that you probably should commit to memory. Is that my phone? Up there? Uh-oh. I always yell at other people for their phones going off. I'm in a class. I'm teaching in a class, so call me back in another hour and a half. Okay. I don't know who it is. Probably a student in one of the other classes, because that's about the only people who've got my number that there. Okay, this is hexadecimal. Now, what I want you to notice about this table is we start with 0, 0, 0, 0, and we get all the way up to F, 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 right there. Our next number, if we were to go through and do the next number on this right here, right here, right here, it would be 1, 0, 0, 0, 0, right there, right? So in other words, we can only go using 4 bits up to the number 15. So what we have is, because hexadecimal can recognize from 0 to 15, in other words, we've got this special race of superhumans that have now got 8 fingers on each hand, right there. So because they've got 8 fingers on each hand, they now count from 0 to 15, right there. And so we're using that there, and it has this really nice, neat little table right there. Now the thing about that is that I can go from hexadecimal to binary by inspection. There's no adding, subtracting, dividing, or anything. Now I can do that. I'm not saying that you can do that yet, but you need to be able to do that. That there. And the way you do that is you put this table down right there. And if I want to convert any number to binary, right here, and I'm just going to write on the bottom here, if I've got the number 2CF4, the binary for that is going to be 0010. It's going to be 1100. It's going to be 1110100 right there. And I get this one from right here. Right there. The 2 right there. You can see the 0010 right there. I get the C1100, I get from right here. Right there. The 1111 I get from the bottom one here. And then 0100 I get from right here. I can do that by just looking at the table right there. And I can convert straight to there. Same thing if I've got the number, binary number, 1100, 1101, 1110, 0010. The first one is going to be a C. The next one is going to be a D. The next one is going to be an E and 2 right there. Again, that's coming straight off the table right there. 90% of what we're going to be using this semester in terms of numbering is going to be in hexadecimal right there. And the reason is because in reality, we're trying to talk to hardware and we're wanting to talk in binary, but binary is too big of a pain in the neck, so we use hexadecimal because it's easier to write, it's shorter, and it's much simpler. And I know that when you dealt with the 8086, you did a lot of binary or hexadecimal, right? Probably enough that where it drove you crazy, right there, right there. And I'm old enough to remember back in the days before assemblers. You know, because last semester you did everything through an assembler, and then you wrote, then you got the opcode. You know, you ran through the assembler, and then it gave you the hexadecimal codes that there. We didn't have the assembler. We had to do the assembly by hand. That there, yeah. And then we actually had to punch it into our development board 1 byte at a time. That there. So if an opcode was 2C, we put 2C enter, 3E enter. That there. So I know how to work with hex numbers that way. I don't want to anymore. You don't want to anymore. Right there. That's why we jumped to C. Is that we let C deal with that there. So, okay. That's there. Let me just jump on to the next one here. Right there. Again, this is just basically says the same thing that I did before. Now, again, if you look at this right here, you notice that he originally wrote that as one big long chain of 12. That there. In reality, we broke it down. You don't see 12-bit numbers very often. The only place that you normally would see a 12-bit number is there's some A to Ds that, for example, will have 12-bit resolution. That there. So normally, most numbers you deal with are going to be 4-bit, 8-bit, 16-bit, 32-bit, 64-bit. But 12 does show up in some applications that there. So again, this is the same process there. So, and then convert to binary first, then hex. Usually, again, most people, what he's saying here, and I have to agree with him, is what most people do if they want to convert from decimal to hex, they go through the binary first. It's easier. Because the process of going from decimal straight to hex is a pain in the neck. So you normally would go to binary first because, again, we take the number hex right there, and that comes out to be 101101. That's 45 right there, and that becomes 2D by inspection right there. So as you go through the process to go from base 10 to base 16, it's easier to go from base 10 to base 2 then to 16. Because from base 2 to base 16 is just inspection. Just like from base that there. Now to go from right here again, same example right there, and it's the same type of process. You can see where I stole the slides from. That's there. Okay. There. Convert from hex to that there. Also suggests the same way is to go through the binary process first, right there. Right there. So you can go easily from the other way, but it does involve the multiplying. If you just convert it to binary first, then you can just simply do the adding, subtracting. That there. So you notice that we skipped the 256, we skipped the 64, we skipped the 8, 4, and 1 right there. We end up right there. So the process of converting back and forth is really easy to go, you know, from decimal to binary and binary to decimal, and then from hex to binary and binary to hex. That there. So everything goes through the binary process. It's just easier that there instead of learning 15 different ways of doing it. Right there. So okay. That there. Now we can do addition, and this is one of the main things that we're going to be doing a lot of is we're going to be doing some number crunching. when we do addition with hexadecimal, keep in mind that we do our carry after F. Right there, just as in my base 17. Here, and let me just jump down here. And let's look at this one right here. Here, we look at right here, our least significant bit here is we're adding our 9 and our 14 right there. Here we're adding 3, right, we're adding 2 numbers. They don't show the line right here. So those are the 2 numbers we're adding. We're adding 9 and 14. E is the number 14 right there. That gives us 23. Then we subtract off the 16, and that's our carry right there. See, 23 minus our 16, that's our carry, and we're left with 7. That's the process that we want to add right there. So if we're going to add, for example, let me just do it here, 3, 2D, 9, and we're going to add 94 BE. 9 plus E is, if we do it in base 10, is the number 23, right? But when we carry, we don't carry 10, we carry 16. That's what confuses people, is our carry is 16. So 9 plus 14 is equal to 23. We subtract our 16, and we're left with 7. So we put our, sorry about that, I keep hitting it. We put our 7 here, and we put our carry right here. That's our carry. Now we're going to add D, and D is what number right there? D is 13. B is 11 plus 1. So we end up with 25. We subtract our 16, we end up with a 9 with a carry. That's a single 1 carry. So 1 plus 3 plus 4 is 8. There's no carry out there. And 2 plus 9 is 11. 11 is the letter B. Right there. Right there. So you will need to know how to do that right there. Hint, hint, there'll probably be at least 1 or 2 questions on the final exam where you're going to be asked to add hexadecimal numbers that they're there. And the same thing with the subtraction, although we don't necessarily subtract terribly often that there. So if we're going to subtract, again, we borrow 16 right there. So in this particular case right here, and I'm going to do a different example here just so that we have a different example here. Let's say we're going to subtract 3, 2, we're going to subtract 1F right there. 1F right there. Well, 2 isn't great enough to subtract 15 from, right? So I have to borrow 16. So I put a 1 here. Well, I'm borrowing 16, so I'm actually 18 is what I've got there. 16, so 8 minus 15, so I've got a 3 is what I've got here. That there. This is now a 2, so I've got 13 hex. So the key thing here is this isn't 12, that's 18 minus 15 is what we're doing that there in terms of numbers that we're comfortable with. That's there. And we'll come back and do some more examples of this in a tutorial session where we go through and work a number of problems like this right there. So we now the next thing I want to talk a little bit about, my throat is hanging on here, that there is numbering systems are exactly that. They're numbering systems. When you have a numbering system, you can add, multiply, divide, subtract. If you have a coding system is different. Coding systems means that these numbers represent something other than real numbers in the sense of a numbering system. An example of that is the ASCII code, which is the codes for the various letters that there. Now this shows the letters from A through Z, capital, and lowercase a through Z, right there. there's also ASCII codes for the numbers 0 through 9. When we're programming, we have to keep in mind that we normally would represent that with a single quote is not the same as the number 0. Right there. Same thing with the number, the ASCII 1 is not the same as the number 1. That there. And that will create multiple problems for more than one person, a programmer. That there is that we need to keep that in mind. Then another coding system, which I'm sure you dealt with in your basic digital course, was something called binary coded decimal. That there, which basically only gave you the symbols 0 through 9, and then when you tried to add, if you had a carry, you had to fill in the missing 6 right there. So binary coding decimal is that there. And you got to remember that when we're dealing with microcontrollers and microprocessors, when we're doing our math, we're doing things in hexadecimal and binary, blah, 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 blah. When we want to output our output for the user to look at, we expect it to be base 10. That there. So it's one of those issues that quite often we have to play games with our data in order for it to make sense for the user. That there. For example, if you're doing a digital thermostat, right? Something very simple, digital thermostat. The temperature of I won't say 5C, that's an awfully warm temperature under Celsius, but we'll say the temperature of 1F doesn't make sense to anybody, right there. You would expect to see a temperature of 23 or whatever it turns out to be, that they're base 10. So you have to take that hexadecimal number and convert it over to binary coded decimal, that there, in order to output it. But all your internal calculations you have to do in hexadecimal and binary, because otherwise math doesn't work. So normally we do the conversion on the output, that there, and sometimes we do the conversion on the input, right there. So we will be doing some practice on that there. Okay. My throat is still holding up barely, but we'll up there. Now let's just get into that there. And this is a review of everything that I consider important in your first semester of digital electronics in 1 hour. That there. All right, voltage levels. This is a critical thing. Now, this is obsolete material. When I say it's obsolete material is because this is based on a 5-volt system, TTL level system. The boards we're actually using are 3.3 volts. So the same concept holds up there. But 5-volt logic is pretty much going away for most modern systems. Now, the 8086 was 5-volt. The 8051s, I think they were using last year, were 5-volt systems. The ones we're using are surface mount. They're tiny little chips up there, and they're 3.3 volts. Almost all modern systems are operating on 3.3 volts or less. I mean, if you look at your iPhone or Samsung Galaxy or whatever you've got, you're not going to find 5-volt signals in there. You're going to find 3.3. But what we've got here is we've got a range from 0 to roughly 0.7 volts right here. So the number 0 actually goes from 0 to 0.7 volts, and this actually represents from about 2.7 volts to 5 volts is considered a high. This range in between is no man's land. If you've got a signal in that level, you don't know what it is, whether it's high or low, and therefore you don't want that to happen. If you measure voltage in this level, something's wrong with your circuit. Right there. It's that simple. Now the exception would be is if you're trying to measure it with a voltmeter. If you're measuring with a voltmeter and you've got a pulse train. In other words, you've got something that looks like this, right there. That's going from, say, 0 to 5 volts, and it's got a 50% duty cycle, and the frequency's high enough, it's probably going to measure 2.5 volts, because it's not going to react fast enough for it to go from 0 to 5, 0 to 5, 0 to 5. So it's going to show somewhere around there. If it's slow enough frequency, then it might very well look at, you might see it go from 0 to 5, 0 to 5. Again, most of our microcontrollers type software, you're going to see things that look like this here. Right there. So, but those are our voltage levels up there. All right. Quick review, and I'm probably going to finish after I get done here, because up there we've got about 4 or 5 basic logic gates. We're not going to do a lot of Boolean algebra this semester. We will do some Boolean algebra, but we're going to be doing it in C and not in hardware. But when we get into interfacing the external memory, we have to deal with some of these up there. We have the Boolean expression for and the output is true if and only if both inputs are true. Right there. Boolean algebra is based on a philosopher. George Boolean was not an engineer. He was a philosopher. And he was actually of, like, I think the 16th or 17th century, long before digital electronics came out. But he developed what's known as Boolean algebra. And it was for solving philosophical problems out there. Had nothing to do with computers right there. So you've got the AND gate and the OR gate right there. Those are our 2 basic symbols that you'll see. AND OR logic is what most people refer to. Then we've got the inverter. This is tri-state buffer, but actually it's the way it's shown there, that is a NOT gate. One thing here to keep in mind that if I'm typing something, I will probably put the inversion as a little dash apostrophe after that there. Some books would put a bar across that there. So there. Then we have the XOR gate. The NOT, of course, just inverts it. If this is a 1, this is a 0. This is a 1 if B or A is 1, but not both. One or the other has to be high. That's the XOR gate. The NAND gate and the NOR gate is just simply a AND gate with an inverter on the output. And this is a NOR gate that's there. One thing very interesting is that, as it turns out, all AND OR logic can be expressed with only a NAND gate or only NOR gates. That's there. So NAND gates and NOR gates are actually much more common than the AND or the OR and OR gates. That's confusing. That there. So you'll have either NAND gates or NOR gates. NANDs are the most common gates out there. And there's a whole family of devices called gate arrays, which is a array of gates right there. And what it is 10 million NAND gates put on a single chip. And then you connect them up however you want in order to get whatever logic you want out there. And right there, we won't be looking at those in this semester. But I enjoy those, but out there. So we've got a couple of other things. I'm not going to worry about this logic here between the half adder and the adder. What's important is the next slide. What's important about this next slide is, you see where I say FA right here? What that's telling me is whatever is in this full adder right here, this is a full adder, that is inside that little box. This is called hierarchical design techniques. So I design a full adder, and then if I want a 4-bit adder, I just tack 4 of those together. And then I could make another box with all this right here. I make a box here, and I call that a 4-bit adder. So then I take 2 of those and add them together, and that's now an 8-bit adder. So I can keep making sub-designs and adding them up there. And that's typically the way digital logic is designed here. That's a little out of this class's realm because we're not going to be doing that type of design. I think in your basic digital course, you probably did get into hierarchical design, where you did sub-designs and added them together. But there you stuck with straight TTL parts, right? That there. Normally, if you're going into this type of design, you're going into some type of field programmable part. That there, and you're using some type of design software such as the Xilinx tools or the Altera tools, or I can't remember the other ones out there. Vector Graphics. There's all kinds of design tools for digital logic where we do this type of work right there. And I spent a good number of years of my career doing a lot of this type of work on the side. That there. So that there. Okay, decoders. And you guys don't take breaks between them. You just keep going straight. That's what I was told. These are 2-hour classes and you just shoot right through and get in after what, about an hour and a half? Is that about what I'm told? What's that? Some instructors go for a full 2 hours. That there. No, you won't see me go for 2 hours. At least not today. You won't see me going for 2 hours. That there. Especially now with the 8 o'clock class. They're not open for breakfast yet. I get a little hungry. Okay. Decoders are very, very commonly used for selecting addresses in I/O ports. Coming out of the microprocessor or microcontroller, you have, in this particular case, 4 bits of an address right there. This here, and we're going to assume it's the upper 4 bits of the address right there. And what this is saying that if the upper 4 bits is 1001, this chip will be selected. If this one here, it's 0101, this chip will be selected. Now this is normally done in this is going to I need to figure out some way to keep this from that okay. Okay, let me kind of go back here. Right here. Okay, let's look at, and I'm going to use a different microprocessor. Let's not worry about what microprocessor I'm using, okay? Let's call it the XYZ processor. And it's got 16 bits of addressing. Right there. Now on the 8086, it had 20 bits. And that's why I don't want to use the 8086. The 8085, the 6502, there's a whole group of processors. You know, most of the 8-bit processors use 8 bits or 16 bits. That's there. So each chip, right, for example, right there, will contain, and for sake of my discussion right here, right there, I'm going to say that each one of these has addresses that go from 000 to FFFF right there. Right there. This is what's inside each of these chips right here. Right there. There. And I can have up to 16 of these chips in my circuit right there. Because 16 bits means that I can go from F, 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 F to 0000. That's my address space that I have there. So in terms of addressing right there, right there, right there, I have right here, this is F, 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 that's the top level. This is F000. There's only 3 zeros there. This next one here is EFFF. This one here goes to E000. And this last one down here goes from 000 to 0FFF. So each one of these is a chip right there, or is a device right there. And what the address decoder does is it tells the chip which one it wants to select right there. So what it's saying, if I want to select this one right here, that's the address of 110 right there. If I want to select this one here, that's 111 right there. If I want to select this one here, that's, and what I'm looking at here, and this is called this right here is what am I doing here? I keep bouncing this here. This is A15, and this right here, A15, 14, 13, 12, right there. So this is 13, 12, and 11 right there. So that sound right? Yeah, 4 bits right there. These are the upper 4 bits of our address bus right there. Right there. And I know you saw this in your 8086 class, but I know that many of you missed that question on the final exam too. That there is what these address coders do is they tell this chip, and on this chip there's a pin on here called a chip select not usually. And that tells that chip that it's being selected right there. And that's what these address decoders are doing here, is right there, is that they're looking at, right there, they're looking at this address right here and say 1001, and we're selecting that chip. Now normally this graph is wrong because normally they would have an inverter on the output, because most chip selects are chip select not. But these decoders are very used, and it's not just memory locations. We're looking for input-output locations. We're looking at selecting, and so we need to decode that there. And as I said, I know it was in your 8086 class you talked a little bit about that, but I just want to kind of hit that point again. Now we won't be using that quite as much with the 8051 because, as it turns out, all of our memory is internal to the chip. We don't have to. There. We haven't talked yet about the difference between the 8051 and the 8086. Right there, the big difference that there. But these decoders are a key part of any system right there. So flip-flops, I'm not going to go into flip-flops. You talked about flip-flops before. Flip-flops are very commonly used for any type of memory storage. Memory is made up of, static RAM is made up of flip-flops. Dynamic RAM is usually made up of other types of memory right there. Usually just static charges that we have to refresh. But flip-flops are used mainly to store data. But we also can design counters out of flip-flops, finite state machines. Does the term finite state machine ring a bell? You ever hear that word before, a state machine? Okay, because I'll be using state machines a lot. That there. You don't like state machines. Actually, state machines, when you use them with C, are much easier. That there. So, okay. I think I'm be honest with you, I'm probably winding down to where matter of fact, I'm really to the point of winding down here to where my throat is set there. I think I mentioned this before. Terminology, this is just kilobyte, megabyte, gigabyte. One of the things that keep in mind that a kilobyte is 2 to the 10th. It's actually 1024. A megabyte, 1,024,000. I mean, they're not exact numbers. A gigabyte is more than a billion memory locations. A terabyte, and I'm old enough to remember my first hard drive was a 30 megabyte. That's there. And my first computer came with 64 kilobytes of RAM. That's there. Actually, that was my third computer. I actually had a Commodore VIC-20 that had 5K of RAM. That's there. So, I mean, when you start looking at some of these old systems, everyone in this room it's hard to believe that these things were that small and that primitive. Only they weren't that small, they were huge. Right there. Okay, I think I'm going to stop here, right there. So, I know we're ending about half hour early, but I think that's pretty much normal for that there. Again, my throat is giving out that there. I think, on the general rule, I'm going to plan on starting about 8:15. Then we'll probably run to about 9:45. Is probably our general rule right there. So, I'm a big believer in that, that you can only absorb how long you can sit and take notes out there. So, I don't have any promises, but